So if we put those year target values back, we see the onset of production in 1917, reaching a peak at around the wartime and falling back, and things were changing at more recent times. And the information that was important was, the question to us was, did the sediment record correlate with what we knew was happening inside the plant? And these names mightn't mean too much to you, but these are the names of some of the ores that were processed inside the plant, and that gave us sort of a new insight into what the sediment record was telling us. At depth, the background signatures rising up, tracking towards a Broken Hill type lead signature. Broken Hill was the sole ore body that was processed at this plant up until the war. Now, of course, the war came, and Tasmanian ore from Rosebery had to be incorporated into the feed, so the signature falls back with that incorporation to more, and it stays pretty constant to more modern times. 1975 was a new environmental awareness. Up until that point, everyone had put their head in the sand and hoped this would go away. No one said anything about it, but the cat came out of the bag in 1975, and no longer could they dump into the river, so stringent measures were put in place, and we can see that change in isotopic ratio because of that, and also new ore bodies from Australia were also brought online at that time in the 1980s. Let's head to Antarctica. So again, just to remind you, here's Australia, and I'm from this little point here, and you can see there's not much between us. It's only a 4-hour flight to Antarctica, or it's a half-week sail. But Tasmania is the staging post to Antarctica, and Australia has sovereignty, or has control, or has custody of about 42% of the Antarctic continent. We take our role there very, very seriously. And there's been work going on the last decade to try and clean up some of the mess that we've made and left behind in Antarctica. So at this station called Casey, which is over in the Windmill Islands over here, there have been 2 bases, or 2 stations, one operated by the Australians called Casey, and one operated by my American friends called Wilkes. Unfortunately, both of these have great waste disposal sites, or tip sites, adjacent to the marine environment. So we take away the map, and yes, Antarctica looks like this, and it's beautiful, but you'll also see adjacent to the coast waste disposal sites where rubbish is just simply dumped, and that's no longer acceptable. So we've been taking marine cores under very difficult conditions off the coast of their stations, and we've been using a very dilute acid, 1 molar HCl extraction, to try and simply extract the anthropogenic, or the contamination from the geogenic base material. And it's very hard to see, but we've gone back every year for the last 5 years and taken cores at the same space, at the same site, and what we've found is that for things like the cores near the Casey station, after the remediation, we're seeing a fall in the metal levels, so things like iron and lead. You don't have to take my word for it there, they're all a bit jumbled up, but we are seeing core profiles that are showing a decrease in concentration of some of these contaminants. And over at Wilkes, where no work has currently been done, you can see they're very consistent core profiles with depth. Also, just showing over near Wilkes, we occasionally hit a real rich where we take a core, we stumble across something like that as we're taking the core, so we'll get a spike of something like there because of that fact. But the take-home message from that slide is that there's been an improvement in the marine environment there. Again, back to lead isotope ratios, and I love looking at these. The same cores, and we've investigated, again, 1 molar HCl extracts from the lead isotope ratios, and these are cores in depth over near Casey. And the first thing we found was that when we looked at the HF digestion, that's the total digestion of both the substrate and what we're interested in, we do see a profile with a slight inflection by that arrow there, you can see that. But when we look at a 1 molar HCl extract, we see a much clearer differentiation in the isotopic record. So this is a very sensitive indicator of the impact of the solution. And over at Wilkes down here, we can see the same thing. Using a 3 isotope plot, what does it tell us? Well, very simply, putting the ring around the Australian lead samples, the samples that are near the Australian base are tracking down towards Australian lead signatures. Nothing unsurprising there, and that's what we expected. Over near Wilkes, where the Americans were, this is their natural background, tracking towards these batteries here that were found at the Wilkes tip site. We still don't know where these batteries came from. We don't know where the lead inside the batteries was from, but it's unequivocal there, with possibly a Missouri signal there. And earlier work we looked at HF digestions of rather than sediment cores, looking at grabs, sediment grabs, surface grabs from the bottom of the bay, which looks a bit like this, which looks like a tip, doesn't it? Background sites where there's no waste like this, fell into this ring, tracking down towards the Australian station. We can see the Australian lead signatures coming out of this background. And over where the Americans had been, even 50 years later, we can see this triangular plot between Australian lead, background geology, and over here, Missouri lead falling on this particular line. So I don't wish to blame my American friends, but if you'd like to help us out, that'd be great. Also, we didn't just look at the sediments. We looked at the macroalgae, the seaweed that was growing in this particular area, and this was a challenge. This is really tough seaweed. If you could cook it up and digest it, it didn't want to dissolve in anything that we really tried. And also the challenge was, if you think about Antarctica, it completely freezes during winter, and as the ice sheet melts over the summer sun, the ice scours the base of the bays and takes all this macroalgae with it and takes it out to sea. So trying to find samples of this seaweed near the tip sites was very hard. But we did, and really what it told us was that these particular samples correlated nicely with the sediment impact from our Australian sources. So it correlated nicely with the sediment record that we previously showed you. So let's have a look at some biogeochemical oceanography. This is work that we've been undertaking the last 8 years. So Tasmania, again, the staging post to the Great Southern Ocean. There's nothing down there, and vessels like this are constantly in Hobart. And 75% of Australia's marine research community is located in my home state. So it's a very important aspect of the work that goes on there. For the past 8 years, we've been looking at methods of analysing trace metals in marine particulate materials. A lot of work elsewhere has been done on the dissolved metals and processes that have been associated with that. But the other aspect of where the metals get provided to the world's ocean is off sources such as land masses, such as dust from volcanoes, from deserts, undersea volcanoes and the sediments themselves, or metals that are actually in the water themselves. And the trace metals, the particulate levels can often be greater than what is naturally dissolved there. And we've been using filters and fractionation and porosity size effects on filters to try various, if you like, fractions or slices of what's floating out there in the ocean. These are some of the elements that we've looked at. These elements tell us stories about where it's particularly come from, whether it's terrestrial or marine. Some of these elements are biologically important, others are more lithogenic markers. And we've been using different filter types of 0.2 microns, 1s, 2s and 54s to collect different material. And this is some data from a number of voyages in 2007 in the Southern Ocean. So you can see here, here's the island of Tasmania, and here's a sampling site that I've just got some representative data here from. The dust, the wind comes from the westerly direction, it always blows from the west, and it never stops, and it takes dust off the island and deposits it out into the ocean, and you can see phytoplankton bloom predominantly over in this side of the coast. And you can see various profiles of metals. I'm not an oceanographer, so I'm not going to try and interpret what that means, except to say that the different profiles represent the processes and that the elements are associated with. It tells us where they come from, whether it's falling from the sky, whether it's coming up from the ocean, whether there's biological activity here at around 50 metres depth, and some of these metals are associated with that. Some of these metals show profiles that indicate remineralisation, life and death, and sinking of the organic and metal matter to the ocean floor. So it's really powerful information for our oceanographers. Heading towards the coast of Antarctica, which you can see here on this particular picture, we've also stepped off the boat and gone and taken core samples through the sea ice, looking at the marine particulate material. And you can see at this particular site I'm showing just by example, in the sea ice, that means it's there in winter, it's not there in summer. We can see these classical L-shaped profiles. Again, the chlorophyll activity indicating biological activity at a depth of near 1 metre. Depth, that's at the sea ice ocean water interface. And many metals follow this classical path, phosphorus, iron, aluminium and so on, indicating that these metals are really involved in the biological activity that's taking place right at underneath the ice. Again, this is really important information for things like climate and biological resources and so on. And I'm going to be talking more about this in a few days' time at Chengdu. Me and the pandas will be there, so I'm hoping to see a few of you along there too. Before I finish, I wanted to also talk about some recent work that we've done looking at a really novel aspect, and this isn't it, but a few years ago we got these little guys. These are gammarids, and these are floating around the coast of Antarctica, and unfortunately we killed a whole lot of these for the name of science, and we cooked them up and we measured their metal profiles, and what we found, the take-home message at that time was that they were really high in iron. They were really high in iron, and that was very interesting, and I didn't think much of that, but the biogeochemical oceanographers, they've taken that and they've said, aha, in the Southern Ocean, nutrients such as iron are really important for phytoplankton growth. These are these little marine plant materials that you see under a microscope, and these are really important because about 50% of the oxygen that we breathe is generated through photosynthesis by these little bits of plant. And these are eaten by krill, and the whales in turn eat the krill. And these are some typical iron levels in krill and whales and so on. And the new aspect was, I don't know why they come to me with these ones, is looking at whale poo. No one had ever done that before, and no one had ever thought of it. But of course, the cycle of life says what goes in has to come out, and my colleagues at the Australian Antarctic Division have been collecting whale faeces and measuring the iron content in these whales, and they've concluded that whale poo is a really rich source of iron which feeds back into the ocean, and the cycle continues. In terms of some facts and figures, about 24% or a quarter of the total iron in the Southern Ocean is locked up in that krill, and the whale faeces, this is amazing, is 10 million times more concentrated in iron than actual seawater itself. Again, I'm not sure how they collect this thing. I think they just actually trawl behind a whale with a net and scoop it up, because I know you're all wanting to know how you do that. So some conclusion, it's magnetic sector or high resolution ICP-MS. I think it is one of the cleanest and simplest ways of measuring elements of interest of low atomic mass that typically are spectrally interfered. And things like I've showed you, iron, copper, zinc, those type of metals, it's a really lovely classical means of doing it. After some early difficulties, I think it is a robust technique. Some of the examples we've thrown at it there, it's able to handle that and a whole lot more. And my approach, my sort of philosophy of doing things as simply as possible, handling the sample as least as possible, as least times as you can, simply diluting it, analysing it in combination with increased spectral resolution, is really a fairly satisfactory approach to solve many problems. And the application, I mean, this is probably where I'm coming from. If you get nothing else from my talk, there are lots of applications right outside our back door that we can apply our techniques, no matter what they are. They're just waiting to be discovered. Just like that whale poo, it's just like a new approach. If we open our eyes, and there's many positive contributions that we can make as scientists to the world around us. I didn't do all this work myself, and I've touched on a number of things, and I don't want to mention all these people, but they've involved pharmacists, chemists, biologists, oceanographers, Antarctic expeditioners, and they do the real work. I've just got to do the analysis with them and for them, but I acknowledge them. I acknowledge my university and my government for funding. Thank you to JAAS. Happy birthday to JAAS. The Union Jack makes me feel at home over here in England. JAAS is more than the UK, but I couldn't help putting that there. Happy birthday to them. And I'll leave you with some pictures from my home, Tasmania. Thank you very much.